Any model that's proposed needs to be supported by experimental evidence, and that's where we're going to connect line spectra to the Bohr model. In this video, we're going to take Bohr's equation for the energy of each orbit and derive an equation that will allow us to calculate the energy of light emitted, so the energy of a photon. And because we know there's a relationship between energy and wavelength and frequency, we can also calculate those variables as well. So let's get started. We know that the energy of a photon is equal to h nu. And the light emitted from an atom is going to be due to the change in energy of an electron in jumping from one energy state to another. So we can say that the energy of that light is equal to the change in energy of the electron. And the change in energy is going to be equal to E final minus E initial. So imagine we have this transition where my electron is starting at some energy and ending at some lower energy. That electron is losing energy and will result in energy emitted and will be less than zero. We'll calculate a negative number, okay, emitted. And on the opposite scenario, we have a low energy initially and a higher final energy. So this energy will be greater than zero and it will be absorbed. So if we knew the energy of the electron initially and finally, we'd be able to calculate that change in energy, which would be equal to the energy of light absorbed or emitted. So luckily, Bohr defined the energy of each orbit according to negative Ry times z squared over n squared. So for the hydrogen atom, z is going to be equal 1. My nuclear charge is plus 1 because I have one proton. So I'm going to bring this equation down for E final and E initial. And I'm going to use some brackets here to break this down. So negative Ry times 1 over nf squared. So we're talking about the final energy. So it'll be the final resting place for my electron. And then we're going to subtract the initial energy. So we have the negative Rydberg unit times 1 over ni squared. And then we can use some algebra to simplify this. So I'm going to factor out a negative Rydberg unit. And then I'll be left with 1 over nf squared minus 1 over ni squared. And just to get rid of this negative charge, just for the sake of making it look nicer, I'm going to multiply the whole thing by a negative and then rearrange so it looks nice. So I'll end up with Ry times 1 over ni squared minus 1 over nf squared. And this equation, delta E equals the Rydberg unit times 1 over ni squared minus 1 over nf squared, is going to be something that we will use from time to time. We can actually calculate the delta E here, which is equal to the energy of the photon, which would then allow us to calculate wavelengths because we know that wavelength is inversely proportional to the energy. Okay, so let's see if we can take this equation that we derived from the Bohr model and predict the wavelengths of light that we would expect to see emitted from the hydrogen atom. So let's look at the n equals 3 to n equal to 2 transition. That's going to correspond to this on my energy scale. From 3 to 2, we're going from high energy to low energy. So we would expect right away that delta E would be less than 0 because that energy is going to be emitted in the form of light. Okay? So that's just a check for us to come back to at the end. We can start plugging in numbers here. Delta E is equal to Ry, which we calculated earlier as 2.18 times 10 to the negative 18th joules. And then we will multiply by 1 over ni squared. So we're starting at this n equals 3. So it'd be 3 squared minus 1 over 2 squared. So this will calculate to 1 over 9 minus 1 over 4. So we can see already that 1 over 4 is a larger number than 1 over 9. So I want to point out that if Ni is greater than Nf, your delta E will be less than 0. Energy will be given off or emitted. If Nf, on the other hand, is greater than Ni, your delta E will be greater than 0, and energy will be absorbed. So that's something, again, that keeps your signs straight in the end. So continuing on here, 2.18 times 10 to the minus 18th joules. This calculates to a negative 0.1389, and that's a unitless number because my n is an integer value that just corresponds to the orbit that the electron is in. And this will calculate to negative 3.0278 times 10 to the negative 19th joules. So this would be the energy difference between the n equals 3 and n equals 2 transitions. So does this make sense? We are calculating a negative number here, and so that tells me that the light energy is emitted, and that is really all the sign is used for. And that does fit with our prediction and what we know about my n transitions. So if we want to then take this and calculate a wavelength, we have to recall a couple of our other equations. We know that E is equal to h nu, and C is equal to lambda nu. So if we combine these and rearrange them, we get the equation E equals hc over lambda. So I can rearrange this and get lambda is equal to hc over E. And remember that this delta E that we calculated here is going to be equal to the energy of the photon emitted. So we can just take this number and plug it in to my formula here. With one exception, we can't carry through this negative sign because that photon can't have a negative energy, right? This sign simply tells me that it's emitted from the hydrogen atom. We want to know just the energy of that photon, and it's going to be the absolute number here. 6.626 times 10 to the negative 34th joule seconds. For Planck's constant, 3.0 times 10 to the 8th meters per second for the speed of light, divided by the energy we calculated, 3.0278 times 10 to the negative 19th joules. So I get joules cancel, second cancel. My wavelength here will be 6.57 rounded times 10 to the negative 7th meters. And if we translate this to nanometers, 10 to the minus 9th meters, 1 nanometer, this would be 657 nanometers. And so that corresponds to a photon in the red region of the visible spectrum. And so if we look at our experimental observations from the line spectra, we can see that there is a red line at 657 nanometers. And so this predicts the emission spectrum of the hydrogen atom exactly. And we could calculate this for other transitions in the visible spectrum. And here's a little hint. Those lines that you see in the visible spectrum are transitions that end at n equal 2. So we could do n equals 4 to 2, 5 to 2, and 6 to 2. And those would be the 4 lines that we see in the visible spectrum. Other transitions will result in UV or IR light being emitted. And we won't see that with our eyes, but it's there. We were just able to calculate the energy of a photon emitted from the hydrogen atom. Now, Bohr's model would also predict that light could be absorbed by the hydrogen atom, and in fact, it is. So if we shine white light on hydrogen in a sealed tube and observe the light that is collected on the other side, we'll find that that light is deficient in certain wavelengths. And those wavelengths correspond exactly with those that would be emitted from the hydrogen atom in the case where it's giving off energy. So we can put energy into the hydrogen atom and see what's called an absorption spectrum. And that shows dark spots where light is absorbed. And we can see the difference between the emission spectrum, which is our line spectrum, and the absorption spectrum, where we see the dark spots corresponding to the frequencies of light that are absorbed. Both atomic emission and atomic absorption spectroscopy can be used to determine an unknown material because they will both give you that unique barcode corresponding to the elements that it's composed of. Another thing that Bohr's model will accurately predict is the ionization energy for the hydrogen atom. So ionization energy is the amount of energy required to actually remove an electron completely from an orbit. So that would be taking that electron and moving it to an infinite distance from the nucleus. So to ionize, we would have to go to n equal infinity. So if we start in the ground state, n equal to 1, and go to n equal infinity, how much energy do we have to put in? I know that it's going to be absorbed because Nf is larger than Ni, so delta E is going to be positive. So it won't take much calculating because the numbers are going to work out nicely for us. So 1 over Ni squared, which would be 1 squared, so that'd be 1 over 1, minus 1 over infinity, which is 0. So delta E is equal to the Rydberg unit, which is equal to 2.18 times 10 to the minus 18th joules. So if we want to completely remove an electron from an orbit, we can put in this much energy. That will take my electron from n equals 1 to n equals infinity, and we'll now have the H plus ion. And that's important, and we'll look at ionization energy trends when we talk about the periodic table in later lessons. We were able to derive this equation that allowed us to predict the wavelengths of light that would be absorbed or emitted from a hydrogen atom. And I'll ask that you're able to use this equation. I won't ask that you derive it like we did, but be able to use it and solve for either energies, wavelengths or frequencies of light, or either of the starting or ending levels that the electron would be at in the atom. So thank you for tuning in and watching this video, and please do reach out if you have any questions. Thanks for watching.